How does that work?
Yeah, you can learn
Of course. Yeah, it's like so wait, how does it just use those? That's not a hard sell. Don't you have to do the whole you do that with just
you should be like teach classes.
这些钱该考试的题，就是介绍那个新型状态研究上主要的经验。
不错。有什么研究方向？有什么研究方向？
就是这些学这就是20年前的现在已经
It's cool. Or you know what I want to do? So you know how Microsoft put their like Excel and their Word platforms are they see access and stuff. I would just like submit something to an Excel spreadsheet, not one.
There's so much
yeah, you're just like, I have just
From the Microsoft. Yeah. And like seriously, like you can provide them with just the spreadsheet. It's like the spreadsheet doesn't have any like right? Yeah, like yeah, so you can just just like copy the HTML and just script and change it. So that
Okay, good afternoon, everybody. I think it's time to start. First, a reminder, the second homework due is next Monday. And then next Wednesday, we will have the second quiz. So after that, we can have a wonderful fall break. Yes. So later, I will make an announcement about the quiz on Wednesday, so that be aware of that. Don't miss the quiz. You can miss the class, but don't miss the quiz. Okay. So let us continue the linear algebra. So in the last lecture, we introduced an important concept called norm. So basically, for vectors, you can consider norms. A norm of vector is the length of vector. Right? So we start with the most intuitive norm called Euclidean norm. So basically, for a vector V, suppose it is a d-dimensional vector. Right? So it consists of d elements. So the Euclidean norm of V is computed as the square root of sum of the square for each element in V. Right? So it's a V1 square plus V2 square with a dot and VB square. So it is quite intuitive. So this is V, right? You can compute the length of V by calculating this square sum of the square root of the sum of squares. And then we generalize this Euclidean norm to LP norm. So basically, when we say LP norm for a vector V, we use a subscript P to denote norm. Right? And it is defined as we sum the absolute value of each element in V into P, right? Plus absolute value of V2 to P, and dot dot dot, and plus until last element is VD to P. And then for this summation, we take 1 over P. So this is LP now. And actually, we can recover our Euclidean norm by set P to be 2, right? So actually, the Euclidean norm is L2 norm. So you can directly verify it. And also, we talk about several special settings for the Euclidean, for the LP norm. For example, when P approaches to infinity, it's called infinite norm. And the infinite norm, namely LP norm when P approaches to infinity, is actually the maximum of the absolute values for the elements in V. So I'll ask you to practice right after the class to show this. It's pretty straightforward. So these are the common used norm definition for vectors, and then we introduced norms for matrices. So various definitions. There are various definitions for matrix norms, and we only introduced the 2 common used ones. The first is called Frobenius norm. So say for a M by N matrix A. Right? So what's the definition of the Frobenius norm? Anyone recall? So what's the notation for the Frobenius norm? If anyone has already started homework 2, I guess it won't be that hard to remember. So first, if we want to denote the Frobenius norm for a matrix, we use a subscript F. And Frobenius norm is pretty easy to compute. It's essentially a kind of equivalent to a Euclidean norm. So basically, you can consider this is an M by N matrix, right? You just flatten the whole matrix into a long vector, then calculate the Euclidean norm of this long vector. This is the Frobenius norm. So for the formal definition, it's actually the sum of the square of each element in A. And then you take square root. This is a Frobenius norm. And another common used norm is called a spectral norm, which is not that intuitive. So to denote a spectral norm for a matrix, we use a subscript 2. But be careful, if inside this norm operation it is a vector, then it is actually a L2 norm, which corresponds to a Euclidean norm. But if it is a matrix, it is spectral norm, which is far from the Euclidean norm. Because the most related matrix norm to Euclidean norm is Frobenius norm. But spectral norm is very, very different. So what is the definition for spectral norm? We actually want to find out maximum value. It's not some, it is some static value, but you need to find it through some maximization procedure. Right? So this is a maximum. Maximum over what? We need to search all non-zero n-dimensional vector. Sorry. Why we should search over n-dimensional vector? Because A is n by n matrix. So we need to search over all non-zero n-dimensional vectors. And then for each vector, we will evaluate a number. In the numerator, the number is the Euclidean norm of A multiplying with this vector x. And then in the denominator, it is the norm of the x itself, which is non-zero. Right? So now we can see why we require this vector x must be non-zero. So, so basically we search over all possible n-dimensional vectors, non-zero vectors, and we calculate the corresponding value, the norm of ax over the norm of x for each x. And then we look at the maximum value and use this max value as our spectrum norm. So this is this one is not very intuitive. But at the end of last lecture, we talked about some geometric view of the vectors. So I want to incorporate those geometric interpretation to give you a some more intuitive meaning for that. So so let us consider the Euclidean norm for a vector u. Right? So how about the Euclidean norm of u multiply a scalar alpha? How does this norm associate with the norm of u itself?
You can pull the scalar out, right?
Yeah, we can move scalar out. But you should be careful, because when you move the scalar out, you have to take the absolute value of alpha, and then multiply the norm of u. It's pretty straightforward to verify this. You can just verify this through the definition of the Euclidean norm. So now, from this observation, let us look at back the definition for the spectral norm. Right? So now we see the norm of ax. This is normal vector because ax ends up with a n by 1 vector, right? Because a is n by n, right? N by n, and x is n by 1. So ax will be n by 1 vector. Right? So this is a norm for a vector, and then divided by norm of x. So the norm of x is what? It's a scalar, right? And according to this observation, we can move the norm of x into the computation of the norm. So this actually equals to 1 over norm of x, then multiply ax, and then take the norm. Right? So now we can move this scalar here. Right? So we can put a here, and then times a new vector that is x over the scalar, namely the norm of x. So now let us take a look at this vector. We can denote it as v. Right? So we denote v as x over norm of x. So what can you say about this vector v? Yeah, it is unit vector. Because we can verify that the norm of v is simply 1, right? Because you can calculate the norm of v will be the norm of x, 1 over norm of x times the norm of x, which is 1. So now we can say v is a unit vector or a direction vector. This is something we mentioned last lecture because its length is standardized, and the only useful information is the direction. So now we can replace x over the norm of x by v, so that we can give a redefinition of the spectral norm. So actually, this is equivalent to maximize over all unit vectors in n-dimensional space. Right? So it is equivalent to find out all the unit vectors in a dimensional space. For each unit vector, we compute the norm of A times B. And we find out the maximum value for such norm and return as the spectral norm of A. This is kind of reparameterization. Any question at this point? So we simply replace x over, because this is our original definition, right? We are simply, so it is equivalent to compute this norm. I will simply replace x over norm of x by a new unit vector v. And then we use this new unit vector v to define our spectral norm. So they are totally equivalent. So now we can take a look at this norm, right? A multiplying with v. So A is a matrix, right? So we can represent A as a set of row vectors. So we can define a set of row vectors as A1, A2 to AM, because A is an matrix, right? It has M rows. So each AI corresponds to ith row. And now when we compute the product between A and V, what's the result? So how can we compute each element of this product? We did it in the last lecture, right? So it actually equals to compute the production between A1 and V, right? And A2 and V until AM and V. Right? This is a row vector, and this is a column vector. So their production is a scalar. Or in other words, each element will be the inner product between the row and the V. Right? And second is A2 V. And the last element will be the inner product between AM and V. So we finally ends up with a n by 1 vector. And then we compute their Euclidean norm, which is the square root of the sum of their squares. Any question at this point? Okay. So now, we know that V is a unit vector, right? So what does unit vector mean? If V is a unit vector, when we do the inner product between vector x and unit vector, what's the meaning from the geometric point?
Projection of x on the v direction.
Yeah, exactly, right? So this is x, and suppose this is v, right? This is the direction of v. So if v is a unit vector, so the inner product between x and v is projecting x onto the direction of v, right? And the projection length is the inner product. So obviously, if the angle is over pi over 2, for example, v is along this direction, then the projection length is negative. So it's actually, you can consider as the length of x multiplying with the cosine of the angle. Okay? This is some geometric interpolation we mentioned in the last lecture. Right? So now we can see that actually the result of the product of A and V, each element is actually the projection length of the corresponding row vector projecting to the unit vector V. So this is suppose this is an n-dimensional space, right? So suppose A have several row vectors. So A1, A2, A3. Suppose that we only have 3 rows. And for a specific unit vector V, say this is a unit vector V. And then what about result A multiplying with V? So the first element of A multiplying with V would be we project A1 onto the direction of V, right? Get the first element, which is the inner product between A1 and V. And the second element in this product would be the projection length of A2 onto V, right? And the projection length, which is A2V. And similarly, the third element would be the projection length of A3 onto V. So those 3 elements consist of the product between A and V. And then we compute the norm of A and V, which is the square root of the sum of the square of those projection lengths. So this is the value for a specific unit vector V. And according to the definition, we want to find out the maximum value of the norm, meaning that we need to enumerate all possible unit vectors. For each specific unit vector, we end up with such a norm. And we find out the maximum norm values, return it as our spectral norm. And then what is the locations for all the unit vectors V? Can you imagine? So V is unit vector. So in n-dimensional space, if length of V is fixed, is 1, right? So all possible unit vector will stay on the surface of a ball, a sphere. Right? So actually, you are looking at let me draw a nice looking ball. Does it look like a ball? A sphere? Forgive my drawing. So actually, you're searching over all the points on the surface of this sphere or ball, right? For each point, you have a unit vector V. And then you compute the projection of all the row vectors on this V and take the square sum and then take the root square. You'll end up with the norm. And when you enumerate all possible points on this surface sphere, you find out the maximum corresponding norm. Okay. You end up with your spectral norm. So this is a little geometric interpretation about the spectral norm. Hopefully that will help you to understand why it is defined like this. And roughly speaking, you can consider that for any specific V, namely a point on the surface of the sphere, unit sphere, or unit ball, the larger the projection length, the more information you can preserve after you're projecting each row of the matrices onto this unit vector. Right? So actually, we want to find out a unit vector which can maximally preserve the information in the matrix after projection. And we use this maximum projection length, not projection length, it's actually the square root of the square of the sum square of the projection length as the spectral norm. Okay. Any questions? Okay, good. So so this is just to help you to better understand the definition, because whenever for some abstract definition, if you have some geometric image or view in your mind, it will be much easier to understand. Right? And the next important concept in linear algebra is called rank. So we first define the rank for a set of vectors. Big X, suppose it consists of n d-dimensional vectors. So namely, each xi belongs to d-dimensional space. I is from 1 to n, right? And then we can define a rank for this vector set. So what's the rank for this vector set? It is defined as the size of the largest subset of X that are linearly independent. So it's kind of a long definition, but it's pretty straightforward to understand. So basically, you just enumerate all possible subsets for this vector set X, right? And you find out the maximum or the largest subset which are linearly independent. Then we use the size of this largest linear independent subset to define the rank of the X. So what is linearly independent? Can anyone recall? Okay. So first, we see linear dependent or linear independent is regarding a specific vector to a set of vectors. Right? So if we say Z is linearly a vector Z dependent on the set X, if Z can be expressed as a linear combination of the vectors in X. So basically, there exists a set of coefficients from 1 to alpha n, right? Each coefficient corresponds to one vector such that they can be expressed as alpha 1 x1 plus alpha 2 x2 plus plus alpha n xn. If there is such a linear combination which is equal to X, which is equals to Z, then we see Z is linearly dependent on X. Otherwise, we see Z is linearly independent on X, meaning that Z cannot be expressed by a linear combination of the vectors in X. Then we call Z is linear independent on X. And then we discuss what is the definition for for a set of vectors which are whether linear dependent or independent. So what does it mean to say that X is linearly independent? What does it mean for a set of vectors are linearly independent? Anyone recall?
So x1 is independent if it can't be expressed as linear combinations of the other vectors in the set.
Only x1?
Or xi.
Yes, you're right? So when we say a set of vector, say x, big X, are linearly independent, means that any vector in this set cannot be expressed as a linear combination of the remaining vectors. So it means that x1 cannot be expressed as a linear combination by x2, x3 to xn, right? x2 cannot be expressed as a linear combination by x1, x3, x4 until xn, right? And you can check for every vector, right? If every vector in this set cannot be expressed by the linear combination of the remaining vectors, then we say the whole vector x is linearly independent. So now, going back to the definition of the rank, we calculate the rank for a set of vectors by finding out the largest subset of x which are linearly independent. Right? Then if x itself is linearly independent, then what is the rank of x? Yeah, it is n, right? Because the largest subset of a linear independent subset will be x itself. So this is rank, the definition of the rank. And then we, based on that, we can define the rank for a matrix. Suppose we have an n by d matrix. Then we define rank of matrix A to be rank of column vectors of A, and also rank of row vectors of A. So there is an interesting conclusion that the rank of the column vectors A is exactly the same of the rank of the row vectors A. So remember, these are two different set of vectors. Right? So suppose A is n by d, right? So the rank, so we can say it's a representation in terms of column vectors would be like a b1, b2 to bd, because it has d vectors, and each vector is n-dimensional. And if you represent it according to the row vectors, we have like a1, a2 to an, right? Because it has n rows, and each row vector is actually a d-dimensional vector. So basically, the rank of the A is the same as the rank of B1 to BD, and also the same of the rank of A1 to AN. You can see the length, the dimension of the vectors in the two sets are different, and also the number of vectors in two sets are different. But this is an interesting property that the rank of the two set of vectors are exactly the same. And regarding rank, another matrix. Regarding the properties of the matrix rank, another important property you should keep in mind is that the rank of the matrix A must be less than or equal to the minimum of n and d. N is a row number and d is a column number. Namely, the rank of the matrix cannot exceed its row number as well as its column number. If if the rank it is the minimum of the row number and column number, then we call the matrix A is full rank. So this is some definition, some basic definition. And regarding the rank definition for a set of vectors, another very important property you should be aware that is the maximum rank of a set of d-dimensional vectors is D. This is something you must have met before in your linear algebra class, but it's easy to forget. But this is a very important conclusion. That is giving you a set of d-dimensional vectors. Right? You can find an arbitrarily large set of d-dimensional vectors, but the rank for this set is at most d. It cannot be d plus 1, d plus 2. It's not possible. And there's an interesting proof to show this conclusion. And I won't have time to show it right now, but if you have time, you can check your linear algebra textbook. And the corollary of this, we can call it lemma, is that if we have a set of d-dimensional vectors that are linearly independent. So let us denote this set of d vectors as x1 to xd. And each d-dimensional vector each vector belongs to d-dimensional space. And suppose this set of these d vectors are linearly independent. And actually we can prove that for arbitrary d-dimensional vector z, it can be expressed as a linear combination of x1 and xd. So meaning that there exists d coefficients alpha 1 to alpha d such that z equals to alpha 1 x1 plus alpha 2 x2 alpha d xd. So meaning that for in a d-dimensional space, as long as I can find out d linearly independent vectors, then we can use this d linear independent vectors to recover any other vector in this d-dimensional space. For an example, I'll give you an example. For example, in a 3-dimensional space. So I can find out a 3 linear independent vectors. What are the 3 linear independent vectors? Axes, right? I can find out 3 linear independent vectors which are the 3 axes, which correspond to x-axis, y-axis, and z-axis. By only using the 3 linearly independent vectors, we can recover any 3-dimensional vector. But no, it is not limited to these only 3 dimensional vectors. You can find an arbitrary 3 linear independent 3-dimensional vectors, and then you can show that for any other 3-dimensional vector, it can be represented as their linear combination. And the proof for this corollary is pretty straightforward if you're using this property. So here, just to give a simple proof. So we can use we can assume that z cannot be expressed by x1 to xt, right? Then we can construct a set of d plus 1 vectors. So z, x1, x2 to xt. So now we know that z cannot be expressed by linear combination of x1 to xt. And similarly, x1 cannot be expressed by all the other vectors. And what's the rank for this set? It becomes d plus 1. And now, according to this theorem, we know that the maximum rank for a set of d-dimensional vectors must be d. Right? So meaning that they cannot be, they must be. That means that our pre-assumption does not hold. So they must be expressed by the linear combination of x1, x2 to xt. So it's simple, straightforward derivation from this theorem. So next, let us look at another important concept about inverse, so matrix inverse. The matrix inverse when we talk about inverse over matrices, we are only talking about square matrices, meaning that this matrix must have the same row number and the column number. If it is not square matrices, then there's nothing to do with the inverse. So we denote the inverse of the square matrix A by A2 minus 1. And then we define that when A multiply its inverse, it becomes an identity matrix. So what is identity matrix? Anyone recall? Yeah. It's a diagonal matrix first, right? So it's a diagonal matrix, and all the diagonal elements are 1. And all the off-diagonal elements are 0. This is called identity matrix. And you can show that if A transpose equals to I, and then you can show that A transpose A equals to I as well. Then we denote this one as the inverse of A. But not every square matrix A has its inverse. So when a square matrix will have an inverse?
If the set of its vectors are all independent.
Yeah, you're right. But more succinctly, we should say the rank of A is full, right? It's full rank. So inverse of A exists only if and only if A is full rank. Meaning that it is important to see that rank of A is n, right? Because we assume A is a n by n matrix. And this condition is similar to like non-zero condition, right? So if we consider a scalar alpha, right, when we compute its inverse, what do we require? We should require that alpha is non-zero, right? And similarly, when we compute the inverse for a square matrix, we should require the rank of the square matrix is full. Right? Otherwise, it's just like 0. You take the inverse over 0, it's meaningless. And if the matrix A is not square, rigorously speaking, there is no inverse. But there is kind of a more general definition called pseudo-inverse, which can apply to those non-square matrices. And the definition will not be covered in this class, but you're recommended to look at their definition. So any questions so far? Okay, everyone looks familiar with those linear algebra stuffs. So the last concept we plan to cover about linear algebra is orthogonality. Orthogonality. So we first discuss the orthogonality between vectors. So if two vectors x and y, their inner product is 0, then we say x, y are orthogonal. So you can also say x is orthogonal to y, or y is orthogonal to x. Nothing different. And from geometry point of view, means that the two vectors are orthogonal or perpendicular to each other, right? So so here is x, here is y, and the angle between x and y is 90 degrees, or pi over 2. Right? And you can easily verify this by using the formula we mentioned before, right? The cosine of the angle is the inner product between the x and y divided by the norm of x and norm of y. And here we're talking about non-zero vectors. Right? If there's zero vectors there, then it's not meaningful here. So if cosine theta, if theta is pi over 2, meaning that the two vectors are perpendicular to each other, right? The cosine theta is 0, right? And then means that this inner product is 0. Then we say two vectors are orthogonal. So here is the one trivial example. So suppose we have two vectors. X is 2 minus 3, 4 minus 1, 6, and y is 4, 5, 3, minus 7, minus 2. How can we conclude whether x, y are orthogonal? Yeah, we just compute their inner product. Right? Just compute the x and y, which is the eigenwise production and summation. Right? So the first eigenwise production is 8, and second is 15, third 12, and fourth 7, and the last is minus 12. Right? So add them together, we end up with 0. So we can conclude that x, y are orthogonal. So now these are regarding the orthogonality between vectors or among vectors. Right? So now let us generalize this concept to matrices. So first, we generalize this concept to square matrices. So for a n by n matrices, we say A is orthogonal if and only if A transpose times A is the identity matrix. This is called orthogonal matrix. And how does this definition for orthogonal matrix associate with the orthogonal vectors? We can look into it, right? So we can first look into the column vectors A. So if we write A in terms of their column vectors, so we have n column vectors, u1 to un, right? So each vector corresponds to one specific column. We have n columns. And then, what is A transpose? What is A transpose? According to the representation here, what's the A transpose?
The column vector from U1 to UN.
Yeah, you just stack the column vectors by rows. You end up with the A transpose, right? So the first row will be U1 transpose. Second row will be U2 transpose. And the last row will be UN transpose. Then, when we multiply A transpose with A, we actually multiply this matrix with this matrix. U1, U2, UN. So this is A transpose, this is A. Then how can we calculate the result element in this product? Yeah. So first A transpose multiplying with A will end up with a n by n matrix, right? Because A is n by n, A transpose is n by n, A is n by n, and the multiplication will be a n by n matrix. So then, how can we compute each element in this product? Just following the matrix multiplication rule. To compute like ith row and jth column, the element at ith row and jth column in this product, we need to use ith row in A transpose and jth row or jth column in A, right? So which is what? Yeah. So here we talk about the edges element, right? So we will use the ith row in A transpose, which is UI transpose, right? And then multiplying with jth column in A, right? So it is UG. So here, this is how we compute the element ij in the result. So now we can say this is scalar because this is the inner product, U and UG. So now let us try to enumerate every element in the result matrix. So how about the first row and the first column?
U1 transpose times U1.
Yeah, it is U1 transpose U1. How about second? The first row, second column.
U2 transpose U1.
First row, second column.
U1 transpose
Yeah.
U2.
U1 transpose U2. And the third column, first row, is U1 transpose U3. And you can enumerate until the last element in the first row will be the U1 transpose UN. And similarly, for the second row, we have U2 transpose U1, U2 transpose U2, U2 transpose UN. And you can compute each row accordingly. And finally, for the last row, we have UN transpose U1. UN transpose U2 until UN transpose UN. This is the result matrix. And because A is orthogonal, we actually know this product is identity matrix. Meaning that this product is identity matrix, so the diagonal element will be all ones, right? And all the other off-diagonal elements are 0. So now we do the mapping. What kind of conclusion can we get? So first, what are the diagonal elements? 1. Yeah, 1. And they correspond to what? U1 transpose U1, U2 transpose U2, U3 transpose U3, until UN transpose UN. So U1 transpose U1 is what? Yeah, it's 1. I know it's 1. What's the definition for that? It's square of the Euclidean norm, right? The square of Euclidean norm. So actually from the mapping from this result matrix and this identity matrix, first we can observe that for each column UI, we know UI transpose UI is 1. Right? And meaning that the Euclidean norm of UI is 1. And second, and this is for all the column vectors. And second, we can look at the off-diagonal elements, right? So the off-diagonal elements are all 0. So what are the off-diagonal elements? They're actually the inner product between two distinct columns. So for arbitrary elements ij, the value at this entry is simply ui transpose uj. I is not equal to g. If I is equal to g, then it becomes diagonal. So now, because these off-diagonal elements are zeros, so meaning that for any distinct two column vectors, ui and uj, where I is not equal to j, their inner product is 0. Meaning that they are orthogonal. This is the definition for the orthogonal vectors. When we say two vectors are orthogonal, their inner product is 0. It means to say their inner product is 0. So now from the definition of orthogonal matrix, what can we get? Two conclusions. First, each column vector has Euclidean norm being 1, meaning that each column vector is a unit vector. And second, any two distinct column vectors are orthogonal. So now we can connect this orthogonal matrix definition to the orthogonal vectors. And the interesting point is that we know for orthogonal matrix A transpose A is it's not 1, it's identity matrix. Then according to the definition of matrix inverse, it means that A transpose is the inverse of A. Right? And it also means because inverse A times A's inverse is identity matrix, right? So it means that A times A transpose is identity matrix as well. So now this is an amazing property for the orthogonal matrix. Its inverse is simply transpose. So if you still have some impression about how to compute the inverse for a matrix, it is kind of a painful procedure, very painful procedure. If you have to do it manually. But if you are lucky to deal with an orthogonal matrix, you don't need to compute it at all. You just do the transpose. You end up with the inverse. And from this definition, we can see that actually the inverse of A exists. So what does it mean? When will a matrix, a square matrix, have an inverse? It is full rank, right? So meaning that the rank of A is n. So it means that the rank for these n column vectors are n. So, and what's the dimension for each of those column vectors? N, right? Because this is an n matrix. Right? Each column vector must be n dimensional. And now we know that for these n dimensional vectors, their rank is n. What can we conclude? Yeah, they are linearly independent, right? It's a linear independent. And they are linearly independent, and also they have the size n. It means that if they are expressive enough to represent any n-dimensional vector, we just mentioned. For any n-dimensional vector, the maximum rank of a set of n-dimensional vectors is n. Right? So now we have this full rank for this n vectors. That means we can use these n vectors to represent arbitrary vector in an n-dimensional space. So what's the usage for that? So we can take a look. Right? So suppose now I have an arbitrary n-dimensional vector z. So because these n-dimensional vectors are linear independent, we know that there must exist n coefficients alpha 1 to alpha n such that we can represent z as the linear combination of these n vectors. Right? So alpha 1 u1 plus alpha 2 u2 until alpha n un. And then the question is, can we compute or can we find out what are those coefficients? Is there any way to find out? Any idea?
You can use a system of equations if you know it's like.
Yeah, this is kind of a general method, right?
Yeah.
So let us consider the special properties for this n orthogonal vectors. Right? So we can try to do the inner product between u1 and z. Right? Let's see what can we find. Right? So if we do the inner product between u1 and z, according to this linear combination, it is equal to what? It is equal to alpha 1 times inner product between u1 and u1. Right? This is a property for the inner product, which we mentioned in the last lecture, and plus alpha 2 u1 u2, the inner product between u1 and u2, right? And plus plus until alpha n times the inner product between u1 and un, right? And now we know those n vectors are pairwisely orthogonal to each other. So it means the inner product between u1 and u2 is 0. And the inner product between u1 and u3 is 0. And the inner product between u1 and un is 0. So all those terms are simply 0. And what about the inner product between u1 and u1? Yeah, it's just 1, right? Because each column vector is a unit vector. So here, u1, u1, their inner product is 1. So now we get alpha 1, right? So alpha 1 is actually the first coefficient. It's simply the inner product between the vector z and u1. So I just switched all, it doesn't matter, right? And similarly, we can get the second coefficient, which is the inner product between z and u2, until the n coefficient, which is the inner product between z and un. So what does this coefficient mean? U1 is a unit vector, right? So what is the inner product between Z and a unit vector? Yeah, projection, right? So the first coefficient, alpha 1, is the projection length of Z projecting onto U1. And second coefficient is projecting Z onto U2. And until the last coefficient is projecting Z to the UN. So what's the geometric meaning for that? So we know we have n orthogonal vectors. So suppose there are only 3, right? Suppose n is equal to 3. So we have U1, for example, here, and U2, and for example, U3. So there are 3 rotated axes, right? You can consider we have arranged x, y, z 3 axes. They are orthogonal to each other, and now do some rotation, but end up with U1, U2, U3. They are pairwisedly orthogonal to each other. And now, given a vector z, if I do the projection on U1, so I get U1 and projection on U2. So I should use the green marker. So get the first projection length, U1, along U1, right? And second projection along U2. And third projection U3. And what do those projections consist of? They actually correspond to the new coordinate in the coordinate system specified by U1, U2, U3. So for a coordinate system, for example, if you have x and y, you want to get its coordinates for any point, you just do the projection, right? So this is the x coordinate and this is y coordinate. So now if you rotate it, say in a new coordinate system, so y prime and x prime. So how do you get the coordinates for this new coordinate system? You do the projection onto the new axis, right? So you do the projection here and projection here. Now you end up with 2 coefficients, 2 coordinates in the new coordinate system. And similarly, for the new coordinate system specified by U1, U2, U3, because they are orthogonal to each other, they form a new coordinate system. And now, if I want to represent the same point z, or same vector z, in this new coordinate system, I need to specify the coordinates. How can I do that? I compute the projection over each of these new axes to get coordinates. So actually, alpha 1, alpha 2, alpha n correspond to the new coordinates of the z in the new coordinate system specified by U1, U2 to UN. So this is some geometric interpretation. And sometimes if U is if the matrix A is not a square matrix, so suppose it is just an n by d matrix, meaning that we only have d vectors. But if those d vectors are unit vectors and also orthogonal to each other, then we call this matrix A is orthogonal. This is called orthogonal matrix. And we only have A transpose A equals to I. We have the same thing, but this is a d by d matrix. You can verify that. And usually, you won't have A transpose equals to I. This doesn't exist. It doesn't hold anymore. if you don't have n vectors, rather you have a smaller number of vectors, then you don't have A transpose equals Y. And you can verify this. So these are the pretty much we need to cover in the linear algebra review. And in the remaining 10 to 10 minutes, I'll show you a few nothing examples doing the matrix computation. Start with the Python 3 instance. So, those code examples are shared in course material. So later you can type them in your Python IDE and play that. So basically, if you want to use Python library to finish those matrix computations, you need to first import the NumPy library. It's very easy to import it following this command. And we can rename this NumPy library as NP, just for convenience. And then to finish some matrix operations such as inverse matrix rank, we need to introduce a sub-library. From NumPy, it is called linear algorithm. So it's just a brief name, right? Linear algorithm. We can redefine as LA. So we can run it. We successfully import these two libraries. And is it clear to everyone? Do I need to enlarge the text? Okay. So we can first use numpy.array function to create the vector. So how we create a vector? Say we create a vector v. We call numpy.array. This is an array function, and the input of this array function is a list. So suppose I want to create a 4-dimensional vector, so I will give it a 4-element list, set 5. And after we execute this command, we have successfully created a vector v. I will print out this vector here. Now let us run it. So it ends up a 4-dimensional vector. And similarly, we can create a matrix, use the same NumPy array function. But if you want to create a matrix, you need to use a nested list. So list of list. So inside this list, the first list will be the first row, the second list will be the second row. So how about the first row is like a 3, 4, 3. And the second row is 1, 6, 7. And we can print out the created array. And it ends up with a 2x3 matrix. Now the first row is 3, 4, 3. The second row is 1, 6, 7. And now to index an element in a matrix or vector, something we should start with 0 rather than 1. This is kind of consistent with C++ language, this kind of stuff. We always start from 0, 1. So the first element in vector v is simply v0, not v1. And also the first element in matrix A is E00. It's not E11. If you want to find a second element, this is E01. So we can. So the second element would be in the first row, V01. You can run it the same. So you see V0 is the first element, 1 here, right? A00 is 3. And A01 is 4. And also we can use slice operation to index a subset or submatrix. For example, we can print out a column. So what does this mean? If we specify the first position by a column, it means that it includes all the rows in A. And then if you specify a second position by this 1, column 3, it means that it includes the column 1 and column 2. So it's kind of open-ended segment, right? So 1, column 3 means that column 1, column 3, column 1, column 2 does not include 3. And also, column 1 here does not mean the first column, it means second column, right? Because it always starts with 0. So we can take a look. What does this return to us? So we can say, the first column means that it contains all the rows, so we have 2 rows. And 1, column 3 means that column 1, column 2 is the second column and the third column. So we can say this is submatrix 4, 6, 3, 7 shown up here. So now by using these slice operations, you can actually pick up any subvectors of matrices from a bigger matrix. And now let us try to define another vector. So here, another 4-dimensional vector, we can call this NP.array function again. It is 3, 4, 2, and 2. And then to add the 2 vectors, we can just using plus. In that we plus 2 vectors together. So pretty straightforward. And then how about the inner product? If you want to compute the inner product between 2 vectors, we can call numpy dot function. And the input parameters are 2 vectors, u and b. And we can run it. Now we can end up with the dot product. And you can verify this is scalar, this is correct. And also, we can do np dot b and u. They are the same. Verify. And also we can call u dot b. This is the same as np dot bu. Now let us talk about the matrix multiplication. So suppose I want to multiply the matrix A. So here is A. So we can say this is a 2x3 matrix. Right? I want to multiply a 3x2 matrix. So let us create a 3x2 matrix. B equals to this one. The first row is 1, 2, and second is 6, 5, and third is 3, 4. And we can print B. So this is 3x2. To compute their multiplication, we use the same function, B dot. A and B is multiply A with B. So we end up with a 2x2 matrix. Because A is 2x3 and B is 3x2, you get 2x2 matrix. And now, if you switch the order, you'll have a different result. It has 3x3. Because B is 3x2, right? And A is 2x3. So we multiply B with A, you end up with a 3x3 matrix. And we can also compute the normal vector by calling the linear algorithm library. So here we define as we rename it as LA. So we can call LA dot norm function over B to compute the Euclidean norm of the D. So this is vector B, right? And when we call this function, we have to compute the Euclidean norm of B. which is this value. If you want to compute other norm, say one norm, we just specify an extra parameter for the norm number 1. So L1 norm is just the summation of absolute values. This out is 15. And also you can call the infinity norm by specify the LP norm. The norm number is infinity. You run it again, then you end up with the largest absolute value. So okay, one last example. One last example is the inverse. So suppose I create a square matrix 1, 2, and 3, 5. If you want to compute the inverse of C, you just call linear algorithm dot inverse C. So you end up with its inverse. And you can check it by the matrix product, right? You can multiply C with its inverse. So now this is the result. You can see that the diagonal elements are 1s, the off diagonal elements are almost 0. The reason that we cannot get accurate result because this is digital computers. You cannot always get you cannot get the exactly correct numbers. There is always some numerical error. And also you can check by like switch the order of the multiplication. You end up with another identity matrix, but with different numerical errors. So those examples are showing the course material. So I highly suggest you to type those code and play the.
Can we use Python for our homework answers as well?
No.
We have to solve this by hand.
Yeah, you should solve. It's not hard. It's pretty easy. Just wanted to refresh your mind about this data procedure. If it is 100 by 100 meters, of course you will need the computers, but it's just a 2 by 2. Okay, we stop here. We'll see you.